Okay, so you either missed lesson 115 or you just want a nice review. I apologize in advance because I have a horrible cough/bronchitis right now. So what we were looking at in this lab is how to figure out which fuel, ethanol or isopropanol, releases the most energy per gram. So the way that we did that was we set the fuel on fire underneath a certain amount of water, and we measured how much the temperature of the water changed by, and we also measured up how much of the alcohol was used during that time. And we made the assumption that the energy released by the fuel was transformed. This was potential energy to start, into thermal energy, and that this thermal energy was being transferred to the water. Now we know there are errors in the setup and that some of the thermal energy is escaping to the air and some is going to the can. But for the purposes of this experiment, we needed to assume that almost all of the energy would go to the water, because if we know how much energy the water absorbed, then we know how much energy the alcohol released. So I'm going to write that out. If we can calculate how much energy was absorbed by the water, we can make the assumption that that is equal to the energy released by the fuel. And that's a huge start to getting toward getting the energy released per gram. Okay, and I also mentioned that we measured how much mass the alcohol lost during that time when the thermal energy was being absorbed by the water. So there will be, that part will be accounted for in our calculations. So first, what is specific heat anyways? Scientists know that for every type of material, there's a certain amount of energy that it takes to change 1 gram of it by 1 degree Celsius, to heat it, I should say. So let's say this is water. This is 1 gram of water, and if I want the change in temperature to go up by 1 degree Celsius, then I need to add 4.2 joules. Scientists have already determined that. If I want the water to cool down by 1 degree Celsius, this would need to release 4.2 joules. So let me quiz you and see if you've got it. What if we have 2 grams of water and we want the change in temperature to go up by 1 degree Celsius? How much energy is it going to take? That's right, 8.4 joules. Or what if it's back to 1 gram again, but you want the temperature to go up by 2 degrees Celsius? Again, that would be 8.4 joules. So you can see that this is going to be a multiplication factor. What if you've got 2 grams of water and you want the temperature to go up by 2 degrees Celsius? Now you're starting to see that what we're doing is we're taking the energy that it took to heat up 1 gram by 1 degree Celsius, joules per 1 gram degrees Celsius, and we multiply. We multiply by the mass of the water, and we multiply by the change in the temperature. So what is that, 16.4 joules? And so, you know, the numbers aren't always this nice. So in this lab, we were heating up 100 grams of water, and the changes in temperature varied depending on how long we were burning the fuel, the type of fuel, etc. So this is in our data. And then 4.2 is always 4.2. That's called the specific heat for water. And again, it's different for other substances. Like oil is a much smaller specific heat because it's easier to heat up 1 gram of oil 1 degree Celsius. So going back to the chem catalyst, water has a large specific heat. What does it mean? It means it takes a lot of energy to heat up water. And the things that we're going to need to collect in order to figure out how much energy a sample of water gains is how much water is there, how much did it heat up by, and we need to know the specific heat of water, which I just told you scientists have determined is 4.2 joules per gram degrees Celsius. So the question that we were studying was which fuel, ethanol or isopropanol, is going to release the most energy per gram. So the thing that we're manipulating is the type of fuel, ethanol or isopropanol, and we're measuring the energy released. We're going to control how high the can of water was above the alcohol burner. We wouldn't want it for ethanol to be like 2 inches away, and then for isopropanol for it to be 1.5 inches away, because that would affect how much thermal energy can escape. We want to keep the type of can the same. We always want to use the same kind of water. Those are some of the controlled variables. I'm going to kind of skip over the calculations for right now because we're going to get to that. It's a good idea to pause and read through those, as well as read through the procedure steps so you're a little more familiar. And let's skip over the practice run. That was an in-class activity. This is what is important for you, especially if you were absent. This is some sample data that you can copy down and use for your lab. Okay, and what I'm going to do right now is run through how to do the calculations. So this will be great for anyone who is going to use their own data. So first trial I want to point out is just this top row. We've got the mass of water, the temperature at the start of the experiment, the end, the change in temperature, the starting mass of the ethanol, the final mass. Again, it should lose mass because that fuel is being converted into energy, and so it's losing mass as it is basically turning into carbon dioxide and water, so the mass isn't just disappearing, but what's also released is some thermal energy. And so this is showing the difference of the before and after. Okay, so first step, we need to calculate what's called Q, the quantity of heat, how much energy was released by the ethanol, by taking the mass of the water multiplied by the specific heat for water, which is 4.2, multiplied by that change in temperature, which is 34. And this comes out to be 14,280 joules. That's how much energy the ethanol released. And then let's get joules into kilojoules because it's smaller numbers, easier to work with. So we're going to take this number and divide it by 1,000. Or you can move the decimal back 3. So that turns into 14.28 kilojoules. And then the last step is we want to account for how much mass of ethanol burned during that process. So we want to divide by the mass used. So we're going to do 14.28 kilojoules divided by 1.3 grams. And that comes out to be 10.98 kilojoules per gram. So every 1 gram of ethanol releases 10.98 kilojoules of energy. But let's look at the second trial. So we're going to do this again. Take the mass of the water again, times the specific heat, times the change in temperature for trial 2, which was 33 this time. And I should put Q at the start. And when I do that, I get 13,860 joules. Again, I'm going to divide that number by 1,000. to convert it into kilojoules, and that turns out to be 13.86. And I'm going to divide by how much mass was burned off, which was 1.29 grams. I'm going to double check. Yes, that's what I remembered from the table. So divide by 1.29, and that is, 10.77 kilojoules per gram. Now let's do the same only for isopropanol. This should be isopropanol. Okay, so first thing we're going to do is write out the mass of the water, which is 100 again, times the specific heat, and times the change in temperature, 43.5. And that comes out to be 18,270 joules. Same steps, divide by 1,000. That comes out to be 18.27 kilojoules. And we're going to divide that by the mass that burned off, which was 1.55 grams. And so that comes out to be 11.79 kilojoules per gram. Last but not least, we're going to take the mass times the specific heat times the change in temperature for trial 2, which was 44. And that comes out to be 18,480 joules. Same steps, divide by 1,000. That makes it 18.48 kilojoules. And then I believe this one was 1.45 grams of isopropanol that was burned off. Yep, 12.74 kilojoules per gram. Final results. Let's find our average. So for ethanol, I got to go back up and look. It was 10.77 and 10.98. So I'm going to add those up and I'm going to divide them by 2. And the average is 10.88 kilojoules per gram released. And let's take a look at isopropanol, 11.79 and 12.74. Divide by 2, the average is 12.27. So now we've got to think about our results, write a conclusion. Start by answering the question, which fuel released more energy? Isopropanol. So I'm just going to say that. Isopropanol released more energy than ethanol. It says use data to support your claim. Cite the averages. So we're just going to say isopropanol released, what was it, 12.27 kilojoules per gram, while ethanol only released 10.88. Then the reasoning section, explain why this makes sense. Try to use the structures. Why would isopropanol release more energy per gram? So this is where I'm going to leave it up to you to say something, well, this molecule is larger, but still it's per gram. But what are some reasons why maybe that one would release more energy per gram? Okay, so kind of make a guess. And then how confident are you in your results? Sometimes groups just, ran out of time, and so they were rushing, and so they don't feel really good about their data. So say something about that. Errors. Did anything go wrong with lab techniques, or, were you not good at keeping the distance the same? between trials because you didn't measure it. What are some ideas you have about random errors versus systematic errors? We can't have all the energy go from the fuel to the water. The can got hot. There's a lot of energy released to the air. So, with our setup, those are errors that need to be acknowledged. Just looking briefly at a couple of these questions, a student who saw the whoosh bottle stated that isopropanol had a bigger reaction. Does what you saw in this lab support that claim? And number 2 confuses a lot of people. Somebody says, we burned a lot of ethanol, it released 1,000 joules. We burned a little isopropanol, it released 950 joules. That means that ethanol releases more energy per gram. Well, what are the units here? I see energy, not energy per gram. And if you're dividing by a big number, like let's say we're dividing by 1,000 grams, and the 950, it says you just burned a little bit, like maybe 1 gram. Well, when you actually consider how much was burned, you're going to get very different answers here. Okay? This is obviously made up numbers, but you kind of get the point that you need to factor in how much energy or how many grams you burned in that process. And the check-in wants you to draw a picture of the can of water with the alcohol burner below it. And it wants you to describe what were the transformations that were occurring and transfers. And so, list them out. I can think of a couple for transformations and then transfers. Oops, transfers. So it wants you to spell that out and draw a picture and show what's going on and name the types of energy as well. So hopefully that helps you out.